Select the major product of the following reaction. So if we take a look at this reaction, we can see that we are starting with an alkene, and specifically we can see that we are starting with an alkene where we have two hydrogens on one side, two alkyl groups on the other side, and so we would describe this alkene as being a cis alkene. And then we want to take a look at what we are reacting the alkene with. So what we've got is a mixture of chloroform, which has a slightly acidic hydrogen because of the 3 chlorines, and we've got a strong base. We've got potassium tert butoxide. So we need to consider what happens when we mix these two things together. So we have 3 chlorines attached to the same carbon, and we have a hydrogen. And we mentioned that the presence of these 3 chlorines is going to make this hydrogen a little more acidic than it typically is. And we're reacting this with a base. So let's draw the structure of the tert butoxide. So we've got a carbon with 3 methyl groups attached to it. And we know that this oxygen is negatively charged because we see that positively charged potassium as the counter ion. So I'm going to leave the potassium ion off of there. It is a spectator. I'm just going to draw the structure of the base. And so this base can remove this slightly acidic hydrogen from the chloroform, which is going to push that lone pair of electrons onto the carbon. And so we are forming tert butanol, right, when this picks up a hydrogen. And that's going to be a byproduct. We're not focused so much on that. We're going to focus on what happens to the chloroform. So we now have a carbon that is an anion. It is a carbanion because we put electrons onto that carbon, and it has 3 chlorines still. And so what happens next in this reaction is we are going to eliminate one of the chlorines. So one of the chlorines leaves, and what that gives us is a carbon that has a lone pair of electrons. It has 2 bonds to chlorine. And that carbon, although it does not have a full octet of electrons, it is electronically neutral. If you were to calculate the formal charge, carbon has a valence of 4, and we see 1, 2, 3, 4 electrons around that carbon. So it is neutral, but electron deficient. This is what we call a carbon that is a carbene. Okay, so a carbene. There we go. So this has a lone pair of electrons, but it is electron deficient. And this means that it is both a nucleophile and an electrophile. So when this carbene reacts with an alkene, it's going to react as both a nucleophile and an electrophile. So let's see what that would look like. So let's go ahead and draw down here. Let's redraw our alkene. And I am going to line up the carbene to react with it. So there is the carbon atom. We've got 2 chlorines, and we have a lone pair of electrons. And so we know that alkenes can be nucleophiles. So the alkene can attack the carbon as a nucleophile. And as we're building up a positive charge here, the lone pair of electrons on the carbene can act as a nucleophile and attack the alkene carbon. So what we're doing here is we are making a 1, 2, 3 carbon atom ring. So this is a cyclopropanation. So we can draw that 3-membered ring. And we should recognize, so let me number these 1, 2, 3, that one of the carbons of that ring is going to have the 2 chlorines. So we go ahead and put them on there. So 2 chlorine atoms. And then on carbons 1 and 2, we've got these ethyl groups. And now in the alkene, they were on the same side. This is a concerted reaction, so those ethyl groups should still be on the same side. So I'm going to draw them as wedges. So they are still on the same side of that alkene. So we started with a cis alkene. And our product, our cyclopropane, is also still cis.